The assumed mean method. Welcome, everyone. Before we dive into today's new topic, let's take a moment to reflect on what we have already covered. In our previous lesson, we explored the direct method, which is the standard way to calculate the mean of grouped data. Now, as you know, the direct method is very straightforward and easy to follow. However, you might have noticed that when we deal with much larger numbers, specifically when the class marks, which we denote as x sub I, and the frequencies, which we call f sub I, become quite large, the calculations can become very tedious. It takes a lot longer, and it becomes much easier to make a small arithmetic error that ruins your entire result. To solve this problem and make our lives much easier, today we are going to learn a more efficient technique called the assumed mean method. This method is designed specifically to simplify those heavy calculations. Understanding the concept. The fundamental idea here is to shift our data. Instead of working with the original, bulky numbers, we subtract a constant value from all of our class marks. Think of it as temporarily moving our entire dataset to a smaller, more manageable range on the number line. By doing this, we significantly reduce the size of the numbers we need to multiply and sum up. This makes our manual calculations much more efficient and, more importantly, less prone to those pesky arithmetic errors we discussed in the previous slide. So, instead of working directly with the actual class marks, which we denote as x sub I, we pick a convenient value to act as our new starting point. We call this the assumed mean, and we represent it with the letter A. Once we have this assumed mean, our next step is to find the deviation for each class mark. A deviation is simply how far away each class mark is from our chosen value. To calculate this, we use the formula d sub I equals x sub I minus a. In other words, we take each class mark and subtract our assumed mean from it. Finally, here is the clever part. Once we calculate the mean of these much smaller, simplified deviations, we aren't finished yet. To get back to our original scale, we simply add our assumed mean back to that result. By doing this, we arrive precisely at the actual arithmetic mean of the original data. In the next slide, I will show you the exact step-by-step procedure to put this theory into practice. Now that we've established that the direct method can become quite a headache when dealing with large numbers, let's dive into the core concept behind the assumed mean method. Step-by-step procedure. First, you need to find the class marks. For every class interval provided in your data, you'll calculate the class mark, which we call x sub I. To do this, simply take the upper limit, add the lower limit, and divide the whole thing by 2. This gives you the exact midpoint of each interval. Second, once you have your list of class marks, you need to choose an assumed mean, which we denote with the letter A. You can pick any value from your x sub I column, but here is a professional tip. Try to pick a value from the middle of your list. By choosing a middle value, you ensure that some of your deviations will be positive and some will be negative, which helps keep the numbers balanced and manageable. Third, we calculate the deviations, represented as d sub I. For every class mark you found in step 1, subtract your chosen assumed mean from it. So, d sub I equals x sub I minus a. Fourth, we need to compute the product, which is f sub I times d sub I. This means you take the frequency of each class, which is f sub I, and multiply it by the deviation we just calculated. Fifth, you'll sum the results. You need to find two specific totals, the sum of all frequencies, which we write as the sigma symbol for f sub I, and the sum of all your products, which is the sigma symbol for f sub I times d sub I. Finally, we apply the formula to get our answer. To find the actual mean, which is x bar, use the formula. X bar equals a plus the quantity of the sigma symbol for f sub I times d sub I, all divided by the sigma symbol for f sub I. Now that we understand the concept of shifting our data to make calculations easier, let's walk through the actual step-by-step procedure you'll follow to solve these problems. In the next few slides, we are going to put this exact procedure into practice using a real-world example involving package weights. Real-world example. Now that we understand the theory behind the assumed mean method, let's put it into practice with a real-world scenario. Imagine a warehouse manager needs to find the average weight of 50 packages. Instead of looking at every single package individually, we have this frequency distribution table, where the first column shows the weight ranges in kilograms, and the second column, which we call F sub I, tells us the number of packages in each range. To begin our calculation, we need to follow the steps we just discussed. Step 1 is to find the class marks, which we denote as X sub I. As a reminder, the class mark is simply the midpoint of each interval. So, for the first interval of 10 to 20, we add 10 and 20 and divide by 2, giving us 15. For the 20 to 30 range, we get 25. Moving down, the midpoint for 30 to 40 is 35, for 40 to 50 it is 45, and for the final range of 50 to 60, the class mark is 55. Now we move to step 2, which is choosing our assumed mean, represented by the letter A. While you could technically pick any value, the most efficient strategy is to pick a value from our new X sub I column that sits right in the middle. This helps keep our upcoming deviations balanced between positive and negative numbers. Looking at our list, 35 is the perfect candidate. So, let's set our assumed mean, equal to 35. In the next slide, we will use this value to calculate our deviations and find the final average. Real-world example, continued. Now that we have identified our class marks and selected 35 as our assumed mean, let's move into the most critical part of the process. Steps 3 and 4, where we calculate the deviations and their corresponding products. Looking at our table, we have our class intervals, the frequencies, and the class marks we calculated in the previous slide. Now, we need to find the deviation, which we call D sub I. To do this, we subtract our assumed mean, 35, from each class mark. Let's walk through the rows together. For the first interval, 10 to 20, our class mark is 15. When we subtract 35 from 15, we get a deviation of negative 20. For the first row, 8 times negative 20 gives us negative 160. Next, for the 20 to 30 interval, our class mark is 25. Subtracting 35 gives us a deviation of negative 10. For the second, 12 times negative 10 results in negative 120. For our middle interval, 30 to 40, the class mark is exactly 35. Since we chose 35 as our assumed mean, the deviation here is simply 0. For the third row, 15 times 0 is, of course, 0. Moving down, for the 40 to 50 interval, the class mark is 45, so the deviation is positive 10. For the fourth, 10 times 10 gives us 100. Finally, for the 50 to 60 interval, the class mark is 55, which gives us a deviation of positive 20. And for the final row, 5 times 20 also gives us 100. Finally, let's look at our totals at the bottom of the table. The sum of all frequencies, which we denote as F, sub I summation, is 50. And if we sum up all our products in the last column, the sum of F, sub I times D, sub I summation, we get negative 180. Keep these totals in mind, because in the next slide, we are going to plug them into our final formula to find the actual average weight. Real-world example, final calculation. Now that we have successfully calculated our total sum of frequencies and our total sum of the products of frequencies and deviations on the previous slide, we have reached the final and most crucial part. Step 5, the final calculation. To find our actual mean, we will use the formula for the assumed mean method. This is expressed as x bar equals A plus the quantity, the sum of F, I times D, I divided by the sum of Fi. Let's substitute the specific values we've worked with throughout this example. We'll take our assumed mean, which we as 35, and add it to the fraction where the numerator is negative 180 and the denominator is 50. When we perform the division, negative 180 divided by 50 gives us negative 3.6. So, our equation simplifies to 35 minus 3.6. Performing that final subtraction, we arrive at 31.4. Therefore, our final answer is, the average weight of the packages is 31.4 kilograms. It is a very satisfying moment when all those individual deviations and products come together to give us a precise result. However, before we wrap up, let's look at some common pitfalls to watch out for in your future calculations. Common mistakes to avoid. First, let's talk about sign errors. This is perhaps the most frequent mistake I see. When you are calculating your deviations, or sub I, or when you multiply the frequency by that deviation to get f sub I times d sub I, please be extremely careful with negative signs. If a class mark is smaller than your assumed mean, your deviation will be negative. If you forget that minus sign during your multiplication or summation, your entire calculation will be off. I strongly recommend you double-check every single subtraction you perform. Second, a very important point. Do not forget to add the assumed mean back at the very end. I have seen many students perform all the hard work, calculating the sum of f sub I times d sub I and dividing it by the sum of f sub I, and then they simply stop. Remember, the value you get from that fraction is merely the average deviation. To find the actual arithmetic mean, you must add your chosen assumed mean, back to that result. Without adding, you haven't completed the formula. Finally, always ensure your class marks are calculated correctly. The class mark, x sub I, must be the exact midpoint of your interval. If you make even a tiny error when finding the midpoint of your class intervals, that error will propagate through your deviations, your products, and ultimately your final mean. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the logic of the assumed mean method, it is very easy to make small computational slips that can lead to the wrong final answer. Keep these 3 points in mind, and you will find this method much more reliable and efficient. Key takeaways. First, let's revisit the purpose of this method. As we discussed at the very beginning, the primary reason we use the assumed mean method is to simplify our calculations. When you are faced with group data where the class marks, or x sub I, and the frequencies, or f sub I, are very large numbers, the direct method can become quite overwhelming. This method acts as a shortcut to keep those numbers manageable. Next, let's talk about the assumed mean, which we denote as a. Remember, this is just a temporary value that we pick to shift our data and reduce the size of our numbers. A great point to remember is that you have the flexibility to choose any class mark from your list to be your a. Whether you pick a small value or a large value, the final result will remain exactly the same. Now let's look at the formula one more time so it sticks in your memory. To find the mean, which we call x bar, you take your assumed mean and add it to the result of the sum of f sub I times d sub I, all divided by the sum of f sub I, and don't forget, the deviation d sub I is simply the difference between the actual class mark and your assumed mean, which is x sub I minus a. Finally, let's consider the efficiency. As we saw in our warehouse example with the package weights, using this method is significantly faster and less prone to error than the direct method when dealing with large datasets. It keeps your workspace clean and your calculations much simpler. All right, we have reached the end of our lesson, so let's take a moment to recap the key takeaways from today's session to ensure everything is clear. I hope this summary helps solidify your understanding. Great job working through these slides today.